I'm back with part two. F, we've got two powers, not the same base. We have to write them with the same base. This one's a little bit more difficult because 27 is not a power of 9. You know, 9 is not a power of 27, but both of these are powers of 3. So if I write them both as powers of 3, then that's the technique. So 27, what's that? That's 3 to the exponent 3. 9 is 3 to the exponent 2, and then now that's got it, right? Because now on the left side, the exponent is 3 times 2x, and this is on the right side 2 times 3x minus 5. We'll see in this one something weird happens here as well, because when I expand, subtract 6x from both sides, so I get all the x's on the same side, I get something that's very strange. The x disappears, and then I get this 0 equals negative 10, which is impossible. It doesn't work. So what does that mean? It means that there's no solutions to this equation. And I want to show you what that looks like graphically. If there's no solutions graphically, what does that mean? Well, on a graph, you know, this is stuff that we might have had from days gone by. On the left side, I've got an equation which is 27 to the exponent 2, I'm going to put that in brackets just so we don't mess it up, 2x in brackets. And then on the other side, I got 9 to the exponent bracket 3x minus 5. And I'm going to just check my windows. That looks okay. Maybe it's not okay. It doesn't matter, but I want to have a look at what this graph looks like. Where's the other one? Okay. And now I can't see it that good. Let's just change it a little bit here. Let's change this to a maximum of 5 so we get in a little bit closer. You see how they're kind of shooting up at exactly the same pace. You know, even though I know this is going to follow an asymptote and this is going to follow an asymptote, you know, these aren't going to cross. This one's going up, this one's going up. They're never going to cross. That means there's no solutions. And so, you know, if that happens, and it will from time to time, oh well. Back to the lesson. We got some roots, and hopefully that doesn't scare anybody, because we know roots mean fractional exponents. And this is similar to the last one where, you know, 16 is not a power of 8. It's not 8 squared. 8 squared is 64. In fact, both of them aren't powers of 4 either. 4 squared is 16, but 4 to the exponent something weird is 8. Both of these are powers of 2. So let's write them as powers of 2. And again, I'm going to write the inside as a power of 2. And have the exponent hanging on the outside like this. So I'm going to write that x on the outside like that. So what's 8 as a power of 2 when I got the square root of 8 actually, don't I? Well, 8 is 2 cubed, so the square root of 8 is 2. The bottom number's got to be the root part, right? Bottom number is the root part. So the square root of 8 is 2 to the exponent 3/2, which this looks a bit strange, but we'll see it's not bad. What about 16? Well, 16 is 2 to the exponent 4. So what's the cube root of 16? Well, the cube root of 16 then is 2 to the exponent 4 over 3. Remember, the bottom number is the root. Bottom number is the root. So this is 2 to the exponent 4/3. And now I can make the exponents equal because I got the bases the same. And I'm multiplying those exponents, and this looks a little bit nerve-wracking to have fractions, but we'll see it's not so bad. And in fact, what am I going to do to get rid of these fractions is I'm going to cross multiply, or I could think about it as multiplying by the lowest common denominator, 6. On this side, 6 and 2 will cancel out, and I'm just multiplying by the 3 anyway. So I can think of this as 9 times the bracket multiply by 2 over here, or multiplying by 6 and canceling with the 3, I'm multiplying by 2. 2 times 4x is 8x there. Hopefully you see that. And then now it's back to grade 9, right? In fact, as soon as this is grade 9 too, grade 9 academic or grade 10 applied, depending on which course you took way back in the day. Subtract 8x from both sides. Like terms here, 10x, and 0 on this side. You could have added 9 on the same step, probably save yourself a little bit of paper. Divide by 10, 9/10. All right, onwards. $500 investment grows by 5% compounded annually. Write the exponential equation that represents A, the amount in the account after T years. So you might hopefully remember vaguely doing this sort of thing last year in grade 11. Remember, A is the amount at the end, P is the principal, I is the percent interest. It's the interest rate per period. And we'll get into some examples like this. N is the number of periods, right? And how's that different than time? Well, remember, if it's compounded quarterly, N is the number of quarters. If it's compounded monthly, N is the number of months. And I is the interest rate that you get every period. So if it was 5% but compounded quarterly, we divide by 4. But we don't have to worry about any of that here because it's compounded annually. Write the exponential equation. Well, okay. That's a $500 investment. And the interest rate is 5% a year. I don't have to divide anything because it's annually. And they wanted me to call this T instead of N because it's just the number of years. And I'm going to tidy that up a bit. And don't be thrown off by the function notation. That's a function. There we go. Find out how long it takes the $500 investment to grow to $1,000. So when is the amount going to be 1,000? And it says use systematic trial. What does that mean? Well, that's the guess and check. Now I want to mention one thing here, that I could just be firing values of T in here and then typing this in and looking for when the output is 1,000. Or I could be smart and tidy this up. I could divide both sides by 500, right? Divide by 500, and then that divided by 500, and this divided by 500. This is just one term. That will cancel like this, and this is 2. So I'm going to look for when this expression on the right-hand side is equal to 2, which is way easier to put in your calculator if you're using systematic trial. Guess and check, right? So for a T, and again, we're just guessing, right? And notice, with the 500 out of the way, my expression gets a little bit easier. 1.05 to the exponent, and this is just a guess, but try maybe 10 years. Well, that's 1.6. For 10 years, I get an output of, maybe I'll just call it Y, because it's not really A at T, of 1.6, right? And so that means I got to go higher. Maybe I'd go 15, and I'm not going to show you all my calculator steps, but 15 was 2.07. So that guess was a little bit high, but close. I'm getting close here. I want this output to be 2 now. I want this output to be 2. So maybe I try 14 years, and that's 1.98. Now I'm getting close, and I see it's between 14 and 15 and closer to 14. So I try 14.2, and then I get really close. And so then I'd say, therefore, it will take about, actually I'm not going to say about, just over, because it's going to be a little higher than this value, 14.2 years to grow. And now notice that this was to double, right? For $500 to $1,000, this is a doubling. And in fact, this 14.2 years and these growth. This is exponential growth, even though it's an investment problem. This is called the doubling time. And we'll see this again later. Give another example? Yes, we do have another example. Radioactive sample has a half-life of 130 days. Make an equation that models this situation. There's the model. Notice the base is a half, so we can see this as a decay problem, and this is a half-life. Half-life, the base is a half. It kind of makes sense. Write an equation that models this situation. Well, the initial amount was 200. The base is a half. I don't have to worry about that. And T is the amount of time that's gone by, and H is the half-life. Half-life's 130 days. Well, there we go. There's the model. There's the exponent. How long until the sample reaches 25 milligrams? Well, this one, certainly I could use, systematic trial where T is here, and then I'm looking for the output to be 25. Or I could use graphing calculator. And this is this sort of technique we saw yesterday, and actually we'll have more practice at this tomorrow, or next day rather, where one side I put in here, the other side I put in there, 200 times 1 divided by 2 to the exponent. You got to watch your exponent here, because all this exponent should be in brackets, x divided by 130, and see where these two cross. Right, and I don't know what the windows. Notice that the windows I'd have to go up as far as 200, maybe 220, because it's going to be decay. It's going to go down fast. Maybe I'll go up by tens or something like that. And what kind of number of days am I talking about? Well, the number of days, it takes 130 days for it just to get cut in half. Well, I'd want to go way higher than that, maybe 1,000 days. Oops. 1100 is not bad. Maybe go up by 200 days each time. And then if I press graph, hopefully I see there's my 25, and there's the crossing point, and I could use the intersect function to do that. But you know what? I'm not going to do that. I'm not going to do it that way that I just showed you, because I'm going to be smart about this. I can see 25, if I just started cutting 200 in half and in half and in half, I'm going to get to 25. So I could think about this logically. Logically, the first 130 days, it's going to go from 200 to the amount is going to be, after 0 days, it's going to be 200. After 130 days, it's going to be 100. After another 130 days, it's going to be half of that. And after another 130 days, it's going to be half of that. I bet you it's 390. Shall we check? Takes days. Shall we check on the graphing calculator? I was right there. Why not? Oh, wow. It's the same. Not always will this logic way work, because this output was kind of a nice value for us, wasn't it? Okay. Lots of problems like that in the homework, and these applications are really why we're doing most of this exponential function stuff, and we'll see them just about every day of the whole unit. So have fun with your homework.